Has ChatGPT ever lied to you? You asked it, "Are you sure?" And it said, "You're right, my apologies," followed by something impressive sounding but wrong. I've been learning a framework for programming with LLMs. It's called DSPy, and it has the potential to make LLMs behave how we'd like them to. This is my quick intro to DSPy and how it can help us get what we want out of language models. In this video, we'll talk about why someone might learn DSPy, what it is, and what it can do for us. We'll look at a realistic use case where DSPy can help us generate multiple choice questions for a kid's math quiz. To wrap up, we'll look at some of the core pieces of the DSPy framework and how they fit together. So let's jump in. Why learn DSPy? What can it do for us? Getting a general purpose language model to behave in a certain way can be quite challenging. It's not easy to make an LLM assume a persona, for instance, consistently, or to ensure that their responses are grounded in truth, not hallucinations. Or if you get things working correctly, the complexity is not manageable. Any changes might drastically alter the output quality. Instead of writing a highly customized prompt that kind of works for the moment, DSPy gives us tools to declare the logic of our output flow, metrics for how to evaluate it, some examples, and then DSPy can figure out the set of instructions or prompt that results in the best quality output. In short, DSPy can figure out how to get the behavior we want, it can help avoid undesirable behavior, and it gives us a lot of great tools for building out our system as programmers and engineers. DSPy emphasizes modularity, portability, and systematically optimizing your language model pipeline to get the performance you'd expect. So how does DSPy achieve that? Two things in particular make DSPy effective. First, with DSPy, the logic of your language model's generation flow is separate from the actual inputs or weights or parameters that go into actually generating a response or output. By keeping the logic separate from these inputs, DSPy allows us to declare how the language model system should behave, what you expect from the output in code. Then, DSPy uses language model algorithms called optimizers internally to figure out the best way to instruct or prompt the system in order to achieve the behavior expectations that we have declared. This modular approach to building and its emphasis on systematic optimization might be why DSPy's tagline is programming, not prompting language models. So when we're thinking about how a language model should act or behave for any particular use case or scenario, it helps to get specific. For instance, this is a list of arbitrary language model response requirements. Some of these are based on actual conversations I've had with real business executives. For instance, there might be words that a chatbot should not use, or maybe it should always include citations in its response. Maybe it should be formatted as JSON. Maybe it should never talk about competitors in a positive light. There's always a trade-off between letting the LLM's intelligence shine through and ensuring that you get what you need and that it's accurate. To achieve these, we might construct an elaborate prompt with some examples, but it's going to be brittle. Any changes to the model or prompt, whatever, might cause it to break. Let's look at a realistic use case and how DSPy might be able to help us. Here, GSM-8K stands for Grade School Math, kindergarten through 8th grade, and it is a public data set. It has thousands of math question and answer pairs. So let's take these question and answer pairs from our math data set and use a language model to turn them into multiple choice questions. Here's an example question. It's a straightforward word problem asking how many yellow flowers there are in a school garden. The answer is 12. This is just an example of what our data set looks like, a question and an answer. So in order to take our question and answer pairs like this one and generate realistic multiple choice questions, what's important to us? Let's say we have some requirements then. We need to ensure that, first of all, the correct answer is included in the output. Otherwise, students can't answer it correctly. Secondly, let's say we want our output to be formatted as JSON to make it useful to us as programmers. Then lastly, let's say that for a multiple choice quiz, we want it to be challenging, so We want to have decoy or incorrect distractor answers that are actually plausible sounding, not obviously incorrect. Normally, language model systems don't guarantee that any of these requirements will be met. For instance, these answer choices aren't actually valid JSON, and one of the answers, D, is obviously quite different from the others. So again, how can we ensure that the language model's output satisfies our requirements? To get what we need, we can compile our language model pipeline into a DSPy program. Here, sample output from a compiled DSPy program satisfies our requirements. To compile a DSPy program basically means to systematically try a whole bunch of things, figuring out the optimal set of instructions like prompt text, demonstrations, even potentially the LLM weights to use when generating new outputs. If I had to summarize what DSPy can do for us in one slide, it's this. It can elicit higher quality responses and avoid undesirable behavior, both of which should make language model-powered systems more reliable and useful. I want to talk a bit about how DSPy works under the hood, continuing with our math quiz example. In a simple DSPy program model like our math quiz question generator, there are just a handful of core parts doing the heavy lifting. I'll say a bit about each of these building blocks in turn. In DSPy, signatures and modules are how we will encapsulate the core logical flow of our output generation pipeline. Modules help us close the loop on training and evaluation in DSPy by separating the logic of our system use case from the actual prompt text and how it gets communicated to the language model. Signatures are used to declare specifications of input-output behavior of a module, sort of like a type signature for our program, is how I think of them. Signatures declare what goes in and what comes out. Let's look at signatures and modules in the context of our math quiz generator. Our module uses an abstracted prompting technique called chain of thought to generate its output. The output is a string of new quiz answer choices. In order to get this output, we state that a number of signature inputs are required for this module, specifically the question being asked, the actual correct answer, and the number of choices we want. So, given these three inputs, the output will be the n total answer choices formatted as JSON key value pairs. We've also defined something called a forward method on our module, which will handle calling our LLM of choice under the hood to do completion, something called prediction here. So these two subclasses of modules and signatures now encapsulate the core logic of our little LLM-powered math quiz generator program, believe it or not. So how do we actually set expectations for how we want our system to behave? This is where datasets come into play in DSPy. A dataset contains examples of our expected behavior, kind of like gold standard examples. We can use these examples in our pipeline, if we wish, to iteratively train and evaluate the quality of our generated outputs. In our math quiz generator code, we're loading DSPy's built-in GSM8K dataset and slicing it into training and dev sets, then labeling the question and answer fields of each pair as inputs. These are Python lists of question-answer pairs, just like the example earlier about flowers in a school garden. We'll definitely need these to ensure that our answer choices are high quality. We also need to define metrics. DSPy needs metrics so it can evaluate the effectiveness of its pipeline's outputs. It needs a way to keep score, so to speak, and so we need to tell DSPy what we care about and how to measure quality. We'll do this by writing metric functions, which we'll want in this case to reflect some of our requirements, such that it be JSON formatted, the answer is included, and the distractors look plausible. And so first we define functions that check various things that we care about, whether or not the answer choices are JSON, whether the correct answer is included, and whether the incorrect answer choices are all plausible sounding. With these helper functions defined, next we add the actual metric functions. The metrics each take as input a gold example along with a pred or prediction, which is basically our pipeline's output. Our code will compare the two and evaluate or score the pipeline with respect to a specific kind of metric. First, an all or nothing score for the JSON format metric. Second, a metric to check whether the correct answer is included. Third, a metric that asks whether the incorrect answers are plausible and says yes they are or no they aren't. With these three specific metrics defined, we now define a top-level overall metric for evaluating the pipeline's output. So, our three requirements we mentioned for this use case are now specified and being evaluated because they are our metric functions. At this stage, we've got a quiz answer generator that can create output, and we haven't even talked about optimizing our pipeline yet. In our code, quiz answer generator is the program defined by our signature and module from earlier, and we're going to load a random question from the GSM 8K math questions dataset to see what kind of output it currently gives us. Our little program will load a random math question, and it produces multiple answer choices. But if you look closely, this response is not actually JSON. It's some text followed by a string of JSON. We'd like only JSON. Our requirements aren't being satisfied, but we need to give DSPy a chance. To find the best way to satisfy our requirements, we'll need to compile our pipeline into a program. In DSPy, compiling means finding the inputs which will produce the highest quality output based on the metrics we've defined. Basically, DSPy tries a bunch of different ways of combining the model instructions, the demos that will be used for teaching, even potentially the model's weights, to figure out how to maximize the system's performance using our target metric. I won't cover optimizers in detail in this video. They're pretty cool and I barely scratched the surface, so please comment if you'd like to see me do an explainer on them. Lastly, you should definitely check out the DSPy official docs. They have a lot of great example notebooks. And if you're curious to see the complete math quiz generator code or try it yourself, I've started a GitHub repository with a few examples of DSPy tutorials. In the meantime, let me know if you have any questions or feedback. Thanks for watching. Take care.